we're still looking at equilibrium, and now we're looking at changes or stresses on that equilibrium. And with that, it kind of falls under the header of LeChatilier's principle. So LeChatilier's principle is that when a change is imposed in a system at equilibrium, so if we have this reaction of nitrogen and hydrogen molecules reacting, forming ammonia, and notice it is in equilibrium. So again, the forward and the reverse reactions are equal. They're at equal rates. Remember, this means equal rates when it's at equilibrium. Again, the concentrations don't have to be equal, but the concentrations aren't changing. They are at equilibrium. However, if we stress the system or impose a change on this system, the equilibrium will shift to relieve that stress or to come back into equilibrium. So let's look at this reaction in particular. So again, nitrogen molecules with hydrogen molecules making ammonia. And notice they're all at gases. So again, this is a homogeneous system. And notice there's heat on this side of the reaction is being produced. So this is an exothermic reaction. If we had a change in enthalpy, it would be negative. Okay, so here's one stress we could do to it. Notice we have our nitrogen, we have our hydrogen in this closed system. And now notice what it says. I'm going to go to the second one here. So notice we have... oh, I made it a little bit too big. I apologize there. Let's shrink it down. Okay, so we have these nitrogen molecules floating around. We have some hydrogen molecules here. And we have one ammonia. Well, notice what happens here. Now we go down and we add some more nitrogen. Well, what is that going to do? Well, if we add more nitrogen molecules, it's no longer in equilibrium. There's too many nitrogen molecules. So the reaction has to kind of balance that out. And how does it do that? Well, by making more ammonia. So shifting, reacting with some of the hydrogen and making more ammonia. So it's going to shift over on the other side. So let's look at the equation, and they have the equation here. And on the side is that if we increase this, so we increase that amount of nitrogen, well, our equilibrium is going to shift to make more of our products over here. And if you noticed in those jars, notice what happened to the amount of hydrogen. The amount of hydrogen actually gets used up and goes down. So if we stress and increase the amount of nitrogen, the concentration, we should say, well, it's going to use up some of that hydrogen. The concentration of hydrogen is going to go down, and the concentration of our product is going to go up. So if we did it in the other way, go in the other direction, so still look at the same thing. Say we increase the concentration of ammonia here. Well, if we increase that concentration, the equilibrium would adjust. It would shift things back towards the reactants. We would make more of these, more nitrogen, and then more hydrogen. So if we increase the concentration of ammonia in this equilibrium, the equilibrium will shift to the left. It'll create more of our reactants. Likewise, here's something we could do as well. That's kind of crazy. Say we removed the ammonia. So we had this in equilibrium, but maybe we did it at a temperature that liquefied our ammonia. So we got our ammonia out of the gaseous state. We brought it into a liquid state, so thereby removing it from the reaction. Well, if we remove something, again, the equilibrium will have to shift to replace it. So if we remove something, these concentrations are going to go down because it's going to shift to the right to replace the ammonia that we removed. Okay, so kind of to rehash this, and we'll look at some other examples as well. If we increase the concentration of something on the reactant side, the equilibrium will shift to the products, make more products. If we increase the number of products, the equilibrium will shift to the opposite side, make more reactants. If we remove one of them, again, let's say we remove the nitrogen gas, we put in something else that reacted preferentially with our nitrogen gas. Well, in that scenario, our equilibrium would have to shift to replace the thing that we removed. So here's something that could be in equilibrium. Silver nitrate dissolving into silver ions and nitrite ions. Well, one thing that I know reacts with silver, silver isn't always soluble. It's actually rarely soluble. If we add some sodium chloride to it, we'll introduce chloride ions into the solution. Those chloride ions will react with the silver and will precipitate out silver chloride as a solid. Thereby, we're removing it from the equilibrium. Well, like we said on the other example, if I remove this from the equilibrium by precipitating it out, then my equilibrium will have to shift to replace that concentration. So it'll shift to the right. It will replace the silver I removed. It'll have to increase the concentration of nitrate, by the way, while that happens. And the amount, notice not the concentration because this is a solid, but the amount of silver nitrate will have to go down. Here's kind of some graphical representation of what happens when we affect that equilibrium. Again, same one we were looking at before, nitrogen and hydrogen making ammonia gas. Notice here's a graph of their concentration over time. So we have these initial concentrations, assuming it's at equilibrium in those initial conditions. Well, notice then we add some hydrogen. So this has been increased. We've added hydrogen gas. Notice what happens is there's an increase in hydrogen gas because we added it. But what happens when the equilibrium gets reestablished? Notice that hydrogen gets used up, and also notice the nitrogen concentration goes down. So if we add more hydrogen, it's going to use up the nitrogen here, and it's going to shift the equilibrium to the product side, and the concentration of ammonia will have to go up. So again, just like we said in the other examples, if we add our reactants, our equilibrium is going to shift to the products, and our product concentration is going to increase. Now, concentration isn't the only thing that can affect our equilibrium. Also, temperature changes are going to shift the position of our equilibrium here. So if, again, we look at this example, notice this is an exothermic reaction. It's producing heat. So it produces heat. Well, if we're talking about LeChatilier's principle, we kind of have to treat that heat as if it was a product. So it's exothermic. It produces heat. If we raise the temperature, we're actually putting stress on this equilibrium. It is just like we're adding that product back in, so we're adding in more heat. Well, what happens to an exothermic reaction at high temperatures? Well, the equilibrium position actually shifts back to the left, and it will actually, in this case, it will decrease this concentration, it'll increase these concentrations, and unlike those previous examples, this one will actually alter our equilibrium constant. So if I wrote an equilibrium constant for this reaction, again, this is temperature dependent, and this is one reason why it's temperature dependent, is because if I alter the temperature of this, it is actually going to shift the equilibrium. If I do this at higher heat, it's going to make more of our reactants. Our products are going to be used up, so this value is going to get smaller. These ones on the bottom are going to get bigger. So for an exothermic reaction at higher heats, the K value is going to go down. Notice now what happens if we do the opposite. What happens if we decrease temperature? Well, if we decrease temperature, just like removing any other product, if I take this out and I run this at a cooler temperature, well, then the reaction will, I hate to use the word, but kind of be more efficient, and will shift further over to our product side. We'll make more ammonia, that concentration will increase, and these concentrations will decrease. So we can affect the equilibrium by changing the concentrations. We can also affect the equilibrium by changing the temperature. Now, again, the important difference is changing concentrations doesn't affect the overall K value. The K value, however, is temperature dependent. So if we do affect the amount of heat, the amount of temperature, then it will affect that overall equilibrium constant. One thing to be aware of when we do this is if we have equilibriums, here we have calcium carbonate, we have limestone breaking down into calcium oxide and CO2 gas. Notice, because these are solids, when we write the equilibrium constant, we ignore the solids in the equilibrium constant because they're not in concentrations. Their concentrations don't alter. So the equilibrium constant for this reaction is completely dependent on the concentration of CO2 gas that is present. So if we change the amount of calcium oxide or the amount of calcium carbonate, it doesn't change the equilibrium. It doesn't affect, it doesn't force the equilibrium one way or another because it's an amount, it's not a concentration. So really the only concentration we can alter to affect this equilibrium is the CO2 gas. So what we could do in this reaction is if we remove the CO2 gas, if we liquefied it, we could shift the equilibrium to replace it. The other ways that this can be affected is this one actually can be affected by pressure changes. So, but only the CO2 gas piece of it will be affected. The other things will not be influenced by the pressure changes. So if we increase the pressure on this one, by the way, let's take it as an example. If I increase the pressure on this reaction, what will happen to the equilibrium? Well, because there's only one gas in it, if I increase the pressure, that's the only thing that it's going to affect. So it's going to put stress on the CO2, and my equilibrium will shift back towards the reactant side, and we'll have a decreased concentration of CO2. Likewise, if we go back to our ammonia examples, so here we can clear it. Notice our ammonia. Let's figure out what would happen if we put pressure on this equilibrium. If we increase the pressure on this equilibrium, Notice we have a nitrogen and we have 3 hydrogens, so we have 4 gas molecules here, and on the other side we have 2 gas molecules. So if we increase the pressure on this, it's going to try to relieve that stress. It's going to shift the equilibrium to the product side because there's fewer gas molecules there. So an increase in pressure will shift the equilibrium to the right. An increase in temperature, again, like we said before on this one, will shift it to the left because in this one, temperature is a product. One other thing to look at is we could have endothermic reactions. Endothermic reactions are going to just be the opposite of exothermic. We'd write the endothermic value over here. Again, that would be a positive change in enthalpy. If I increase the temperature for an endothermic reaction, well, then that will shift the equilibrium to the right. It'll use up that temperature, essentially. If we run it at a really cold or low temperature, if I do it at a low temperature, well, then it's going to shift to the left. So a low temperature is going to shift to the left. A high temperature, it'll shift to the right. Okay, let's answer a few questions from your section review. Predict the effect that a decreasing pressure would have on each of the systems. So A, what would happen if we decrease the pressure? Well, if we look closely at A, we'll see hydrogen and chlorine on one side, hydrochloric acid on the other. They're all gaseous. Okay, so pressure will affect this equilibrium, but because there's 2 gas molecules here and there's 2 on the other side, it's going to have no change because there's the same number of gas molecules. So an increase in pressure is really not going to affect this equilibrium, or decrease in pressure, I should say. In the second one, this is a solid, ammonium chloride. On the right side, our products are both gases. So a decrease in pressure, like the question says, will actually shift the equilibrium to the right to replace those, not to replace those gas molecules, but because there's really more space. So a decrease in pressure will shift the equilibrium to the right. Notice this one. This is aqueous. Solution is not going to be affected by pressure. Liquid's not going to be affected by pressure, but our oxygen gas will, and it's on the product side. So again, a decrease in pressure will shift our equilibrium to the right. Last one, 3 gas molecules and 2 gas molecules. A decrease in pressure here will actually allow the equilibrium to shift to the left, to the side where there's more gas molecules. Okay, one more question, 6. We have solid carbon reacting with oxygen gas to form carbon dioxide. So carbon plus oxygen, we're forming carbon dioxide. We'll assume the carbon dioxide is a gas, the oxygen is a gas, carbon is a solid. Okay, and it's balanced the way it is. Notice 393 joules of heat are released. That means it's a product. I'll put it over here. Does this reaction become more favorable or less favorable as the temperature decreases? And again, this is in equilibrium, so if the temperature decreases, we're essentially removing heat from this reaction. If we remove heat, the equilibrium is going to shift to replace it, so it's going to be more favorable.